The colors produced on bubbles in the sunlight is a beautiful example of what is known as thin film interference. When white light reflects off of the surface of the bubble, it disperses into its wavelengths. These wavelengths all interfere with each other, and we see different colors and brightnesses on the surface of the bubbles. Using monochromatic light means that a single ray of single wavelength light will hit the surface of a bubble, and there will not be any dispersion as there is with white light, made up of many different wavelengths. The monochromatic light ray is traveling through air and hits the surface of the bubble. Our air layer has an index of refraction of 1, as does the air inside of our bubble. And for right now, we want to define the index of refraction of our bubble layer as more than 1. Some of the light is reflected by the surface, represented by ray 1. The index of refraction for the bubble layer will be more than the index of refraction for the air, so we can say that the light is essentially hitting a fixed surface. A light ray reflected by a material with an index of refraction greater than that of the material in which it is already traveling experiences a phase shift of 180 degrees. That is, upon reflection, the light wave flips over and the crests become troughs. So a phase shift acts just like a path difference of a half of a wavelength. The rest of the incident ray enters the surface of the bubble, and since the index of refraction is more than the index of refraction of air, the light ray will be bent towards the normal. This ray will be transmitted through the surface of the bubble and eventually hit the boundary between the bubble and the air inside. This boundary layer will reflect some of the light back through the layer of the bubble. When it reaches the boundary between the bubble and the air, it will again refract, only this time it will bend away from the normal. The result ends up being that ray 2 leaves the bubble on a path parallel to ray 1. So ray 2, even though it is traveling at the same angle as ray 1, has had to travel an additional distance through the bubble layer before finally going on its way. If we call the layer of the bubble T, the effective path length of ray 2 ends up being 2T longer than ray 1, since it has to travel through the thickness of the bubble twice. Unlike ray 1 that reflected off of a layer with a higher index of refraction, ray 2 is going to reflect off of a surface with a lower index of refraction. This means that ray 2 will not have a phase shift occur. Now, if the extra distance that ray 2 travels causes the wave to have a phase shift of its own, then the two rays will be back in phase and constructive interference will occur. So if the extra distance traveled by ray 2 is equal to half of the wavelength, it has undergone a phase shift and is now in phase with ray 1. This will actually be true for any multiple of the half wavelength. When you see the bright colors reflected off the surface of a bubble, this is what is happening. However, if the thickness of the bubble is such that the distance traveled by ray 2 is the same distance as some multiple of an entire wavelength, then the two rays are exactly out of phase and will destructively interfere with each other. This is where no reflection appears, and the area appears dark and you can see through the bubble. Something to keep in mind is that since the index of refraction is higher in the bubble layer, we can say that the speed of the wave is slower than the speed of the wave in the air. We also know that the speed of the wave in anything is determined by the frequency of the wave and the wavelength of the wave. Since the frequency of any given wave is determined by its source, that must mean that the speed of that wave in a different media changes the wavelength of the wave. So our wave traveling through the bubble layer slows down. Since the frequency stays the same, then the wavelength must be shorter inside the bubble layer than it is in the air. When we compare the wavelength to the bubble thickness, we are talking about the changed wavelength inside the bubble, or lambda sub n. We have already talked about how the wavelength in a new medium depends on the original wavelength divided by the index of refraction. Since it is often more convenient to refer to the original wavelength, we can substitute that expression into our interference expressions. For constructive interference, this works out to 2 times the thickness of the layer equal to the original wavelength divided by the index of refraction times 1/2, or 3/2, or 5/2. Any multiple of a half a wavelength is going to give us constructive interference and bright colored reflections in this situation. For destructive interference, the path length difference must be equal to an integral multiple of the wavelength. It is also worth noting that this includes a path length difference of 0, since that would indicate that the two rays are right on top of each other. Now here's an important point. When light reflects from a medium having an index of refraction greater than that of the medium in which it is already traveling, a 180 degrees phase shift, or half of a wavelength, occurs. So when a film is very thin, the path length difference between the two rays is negligible. They are exactly out of phase, and so destructive interference will occur. Note this is only true if the index of refraction for the second medium is greater than that in which the light is originally traveling. If the index of refraction is less inside than the surface that it is reflecting off of, then the wave will simply bounce off of the surface in phase with the light coming in. This is important to pay attention at every boundary involved. So we have a soap bubble that appears green on its surface. What is the smallest thickness the soap bubble film could have if the index of refraction is 1.35 for the soap? So we can assume the light is reflected perpendicularly from the inner surface of the bubble. The path difference of these two rays is defined as 2t, where t is the thickness of the soap bubble. So ray 2 travels a distance 2t further than ray 1. And since the index of refraction of the soap bubble is higher than that of air, ray 1 undergoes a phase change as it reflects off of the top surface of the bubble. Ray 2 does not undergo a phase change as it reflects because the air inside the bubble has a lower index of refraction. In order to determine the thickness, t, required for interference maximum, we need to use the wavelength of the light in the soap, which we can find since we know the original wavelength and the index of refraction. So the phase change at only one surface means that in order to have constructive interference, the minimum path difference is 1/2 of the wavelength inside the soap. Plug in the numbers that we know, and we find the minimum distance is 100 nanometers. So this is the smallest thickness our soap bubble can possibly be in order to show bright green light on its surface. If we are interested in the next thickness, where we would see the bright green light reflected, we would need to use the next half order, or 3/2. Essentially, we would just be multiplying our smallest thickness by 3, and we would find 300 nanometers would also reflect the green light. We can use this idea of thin film interference to help us with our cameras. Sophisticated cameras use a series of several lenses. Light can reflect from the surfaces and degrade the image clarity. And so to limit these reflections, lenses are coated with a thin layer of magnesium fluoride in order to cause destructive interference at the surface of the lens. So what is the thinnest film that can cause destructive interference if the index of refraction is 1.38 and it is designed to limit the reflection of 550 nanometer light? So light is traveling through air with an index of refraction of 1 and hits the magnesium fluoride layer on the lens of the camera that has an index of refraction of 1.38 before traveling through the glass with an index of refraction of 1.52. The light ray of 1 will reflect off of the fixed surface of the magnesium fluoride, since the index of refraction of magnesium fluoride is higher than that of air. So the reflected ray will undergo a phase shift. What is important to note here is that ray 2 will also undergo a phase shift because it is reflecting off the surface of the lens, which also has a higher index of refraction than the magnesium fluoride it is traveling through. So in this case, both rays undergo a phase shift, which means that in order to have destructive interference, we will need to use the equation that is half a wavelength off. Let that sink in for a minute. Then we can solve that equation with our numbers, and we find that magnesium fluoride film needs to be a thickness of 99.6 nanometers. Obviously, for something like a camera that relies on light coming in to do its job, we would want to use the smallest thickness we could get away with. These films are called non-reflective coatings, and we find them not only on lenses, but on things like car windows and sunglasses as well.